Thanks, David, for the nice welcome, and I'm so glad to see so many old friends and some new ones here today. You know, the room may be crowded, but this is my absolute favorite lecture room on the whole campus. I've taught here a number of times, and isn't it wonderful? All this wood in this really old building. Perfect setting to talk about the past and the future of this, the Bay Area and the Bay. Sunrise over San Francisco Bay here is a perfect opening for this short course on its future. And today we're going to look at some of the challenges of the Bay and think about what the sunrises might look like in 25 or 50 years from now. This photo and others I'll show you this morning are by John Karachewski, who's a wonderful geologist and a marvelous photographer who also did the photos for my book on Bay Area geology. I should say it's not on San Francisco Bay, it's on San Francisco Bay Area geology, and UC Press does have a book on the Bay that's, I think, in production. But John's sitting over there, and John, wave your hands in case you want to ask him any questions about how he took this wonderful picture. He'll tell you about an early Sunday morning before Christmas when not only was the Golden Gate Bridge empty where he took this, but as you can see, so was the Bay. And you don't see the Bay empty like this of boats very often. So catch John at lunch and he'll tell you about this. We live in around a truly remarkable body of water, which is the centerpiece of our lives. It is the central to the quality of our life and, of course, to the economics of the whole region. So what happens to it in the future is of critical importance, and that's one reason we're talking about it today. Much of what makes the Bay remarkable, however, is invisible, hidden to the eyes of the multitudes who cross the Bay and work along its shores every day. We're all familiar with it, and we probably think we know it pretty well, because I doubt that any of us who live west of the East Bay Hills or east of Peninsula and Marin Hills don't look at it every day. I see it whenever I walk anywhere from my house or from campus. It's there and part of me. But it has its secrets, and there's a lot to the Bay that's not obvious when you look at it in a picture. It looks deep. It looks as deep as the ocean to the west, but in fact, it's not deep at all. It looks like it's been there forever, but it hasn't. And although Dave referred to a history going back millions and millions of years, this bay is very, very young, as we will see. And it looks permanent, though, as you've heard, it has come and gone over the million years, and through most of its history, it was actually a dry valley, not a body of water. San Francisco Bay is an estuary, which is a place where salt water from the ocean, here coming through the Golden Gate, meets fresh water coming down from the river systems and joining and mixing with the salt water. And I should mention that most of the mixing takes place up in the northern reaches, historically in San Pablo Bay, but as we've withdrawn more water for agricultural and metropolitan uses, the mixing zone is often in this region here, and during droughts the salt water may extend as far upstream as the delta. The South Bay is an interesting kind of appendage. 90% of the fresh water that flows into the South Bay comes from not the streams like Guadalupe River, but comes from sewage treatment plants. Only 10% of the fresh water flowing into the South Bay actually comes from natural runoff, unlike the Northern Bay. Now, estuaries are very challenging environments, as you can imagine, because organisms living in them have to deal with a constant change. They're the daily tidal cycles, two of them. They bring salinity and temperature changes, as do the seasons. Much hotter in the South Bay, warmer the South Bay in summer than in winter. And now we also have, through human intervention, the physical and chemical pollutants that we dump into the bay. And of course, the filling we've done around the margins. So this means major challenges for the organisms that live in the bay, for the bay's ecology, particularly, but not exclusively, along the shoreline. The drainage basin of the waters that flow through San Francisco Bay, are really surprisingly large. The rainfall and snowmelt from 40% of California flows through San Francisco Bay to the ocean. You can see here most of it coming from the tributaries to the Sierra and the northern the Klamath up here and even up into Oregon. And the story of San Francisco Bay really starts with the snowmelt and rainfall in the Sierra. There are also streams that flow east into the Central Valley and the Sacramento and San Joaquin river systems, but they tend, with a few exceptions, they're ephemeral streams that are only active during the winter rainfall. But you can see what a very, very large area, and not only the snowfall and the rainfall, but the pollutants from this huge drainage basin. As I've indicated, the bay has its surprises. And one of them is its bathymetry, as you can see here. You don't see it when you're sailing on the bay or crossing on the bridges or enjoying it from the hills, the view. But the fresh water that comes in from the rivers flows into a very, very shallow bay. The average depth is about 5.5 meters. That's about 18 feet. 2/3 of the bay is less than 12 feet, less than 3.5 meters. And all of the white area that you see, which is much of San Pablo Bay and a large part of the South Bay here, is less than 2 meters, and this is an average at mean tide. So at low tide, these white areas are sometimes only a foot or two deep. And I had a friend who lived up on Days Island, right up here at the north end of San Pablo Bay. And these friends would sit out on their deck, gorgeous view at sunset, or, and more than once, they would be hailed by a fisherman in a rowboat or small boat who hadn't paid any attention to the tide charts, had motored into San Pablo Bay to fish. Tide goes out, boat gets hung up, calls for help. The people wave their drinks and say, sorry, we can't get to you. The tide will come back in 6 hours. So if you don't know how to read tide charts, take a good book. You actually could walk across San Pablo Bay at low tide with your head above water if you're not too short. And if the surface of the bay was hard enough to hold you up. It isn't. It's goopy. It's softer than soft ice cream, and you would sort of sink down into it. But it's that shallow. And the bay is as you can see, a very, very shallow feature. The only deep areas are the channels here, which we'll talk about, and this area in this triangle between Angel Island, Alcatraz, San Francisco, and the Marin Headlands. The rest of the bay, think, very, very shallow. Now, if you had gotten into your time machine as recently as 8,000 years ago, you would have had another surprise. You could have landed your family time machine almost anywhere in this whole picture on dry land. Because at that time, what today is a bay was a dry valley. And in fact, the shoreline was way out here off the edge at the edge of the continental shelf. Large mammals roamed around this dry valley. It was grassy, and there very well may have been humans camped along the shores of the mighty river that flowed through it, bringing the drainage out here, as we'll see in a minute, and camped along the creeks draining the Bay Hills. But go back further in time with your time machine to about 120,000 years ago, and you would have again seen water, only a very large bay, bigger, colder, more marine than the one we have here today. So another surprise. The bay is not permanent. It comes and goes. And this bay that we have today is very, very young. None of that you see when you look at it as from the bridges. The bay is a product of a particular geologic and climate condition at an instant of geologic time. And to understand the future of the bay, we really need to know something about its past, and particularly why we have a bay here at all. So, another of John's gorgeous pictures. Think about this as a dry valley, and to drain all of this water out of the bay, and think about what it would have looked like when it was a dry valley. Note also here Raccoon Straits. We're going to come back. That's a very important feature. So let's take a look now at some of the geologic processes that form the bay. The two most important ones are the tectonic movements, that is, movements of the crust related to faulting that fold and fault up the crust and shape our landscape of hills and valleys. And the other major one is changes in sea level rise and fall as we go in and out of ice ages, and that affects whether the bay is a bay or whether it's a dry valley. I think you all know that we live at one of the most dramatic geologic settings possible in the world, and that's a plate boundary. The San Andreas Fault here is the sliding boundary between the very large Pacific and North American plates, and the Pacific plate sliding past the North American plate at the rate of 2 inches or so, an average rate 2 inches a year. It's about how fast your fingernail would grow and how much it would grow if you didn't cut it regularly. But of course, as we know, that movement it takes place in big jumps, many inches, sometimes many feet at a time in an earthquake. But the dominant movement is sliding, and if you wait long enough, maybe 10 million years more or less, Los Angeles will be our neighbor to the west. This movement in the Bay Area is along a whole range of faults. This slide shows the dominant faults of what's called the San Andreas fault system. The boundary between plates, particularly our sliding boundary, is not a narrow single fault. We refer to the San Andreas fault, the main San Andreas fault here, as the plate boundary, but that's for convenience only. The actual plate boundary, the interaction between the plates, it affects not only the whole Bay Area, but there are faults related to the plate boundary extend east of the Sierra Nevada and across the Great Basin. So it's pretty simplistic to think of the San Andreas Fault as the plate boundary, but it's easy to do. In the Bay Area, we have these dominant faults that you can see here, and you can see that the bay itself is a tectonic valley between the Hayward and the San Andreas faults. Parts of the bay downdrop more than other parts, but basically a low spot in our Bay Area topography. This slide also shows you the epicenters of the 1906 and the Loma Prieta 1989 earthquakes. You may think of the epicenter of that as up here at Olema, but in the 90s, seismologists from Berkeley here looked at the data again from the 1906 earthquake and located it on a small branch of the San Andreas Fault here off of Lake Merced. So these are the main faults that today are affecting the Bay Area and creating the bay. Now, without these faults, we might live in a landscape that's as wet as Kansas, with its gorgeous fields of waving grain, but far less interesting and complex geology. It's these faults that make our Bay Area so interesting. Okay, so now there's another wrinkle. The dominant movement, as I've said, is the Pacific Plate sliding past the North American plate here at the rate of the average of a couple of inches a year. Beginning about 3 or 3.5 million years ago, there was a slight change in the plate orientations in the western U.S., and that resulted in a little bit of convergence between the Pacific and the North American plates, so that there is a small element of collision, if you were, of squeezing between the Pacific plate and the North American plate. They're not just like this, I think you can see, but slightly like that. And that motion is in that small component, about 10% of the total movement between the Pacific and North American plates is this convergence. The other 90% is sliding. But that little bit of convergence is enough to bring us our wonderful hilly Bay Area landscape. That combination of sliding and a little bit of compression is called transpression. And transpression is the main process which is shaping the Bay Area today. It involves two kinds of deformation of the crust. Folding, here is folding of the crust into hills and valleys. This could be the East Bay Hills here that are being folded up as we speak at the rate of perhaps 1/16 of an inch or so a year. That's about 1 millimeter or a little bit more. And if there happens to be an earthquake, while we're sitting here today, the first thing you want to do is watch out for things here, although they've been well bolted, but get under your desk, protect your head. The second thing to do is to think, oh, the East Bay Hills are going up again. The The hills are young. They're more or less 1 million years old. This squeeze play only started about 3.5 million years ago, and it's taken only that long to fold up the Bay Area landscape and produce the hills and valleys that we have. The second mechanism is faulting that you can see here. A thrust faulting is a low angle fault, here shoving this piece of the crust up and over this piece. You can see this layer was once contiguous with this one. And if I were redrawing this figure, which is done for the geology book, I would put a big row of hills right here to indicate that this is really sliding up in the air. This kind of deformation of the crust is what's pushing Mount Diablo up into the air, and Mount Tam, and many of the hills around the South Bay. Also very, very young. Mount Diablo was not there at all 4,000 years ago. An ash flow from the Sonoma, the volcanoes that were perking along up in Sonoma and Napa counties, flowed south across what's today Carquinez Straits and Mount Diablo, where Mount Diablo is, and their deposits of those south of Mount Diablo tells us that neither Carquinez Straits nor Mount Diablo was there at that 4 million years ago. So again, a very, very young topography. So you look at this now, look at it with a little different light. It's clearly not Kansas, but 4 or 5 million years ago, it looked very, very different from this. This is a young landscape, a even younger bay, but a very young landscape. And these hills, these lined up, here's Diablo on a thrust fault, Mount Tam. I suspect Hamilton too, but we don't have the evidence yet. Note also this bend in the San Andreas Fault here. That's producing a kind of a squeeze play between this part of the Pacific Plate and this part of the North American Plate, again, to be really local about it. And it's that bend and that squeeze play combined with the slight angle of between the Pacific and North American plates that produce these mountains, the peninsular, the Ben Lomond Mountains, the peninsula ranges, and ultimately the Loma Prieta earthquake. So a very young, dynamic, moving all the time landscape. This slide shows you again how these hills have wrinkled up. Rocky Ridge here, this is taken from Mount Tamalpais and Rocky Ridge, and behind it, the next ridge is way in the distance, Mount St. Helena. But you can see these ridges and valleys line up more or less parallel to the Bay Area's fault system and are shaped by movement on all these faults and the wrinkling up of the Bay Area. One other process that's shown so well in this slide that I want to mention, it's not just folding, faulting that shape the landscape as a whole, but also weathering and erosion. And this large deposit down here and these around here on the north side of Mount Tam are landslide deposits. Prehistoric, huge amounts of the northern face of Mount Tam slid down and created this very rumpled kind of topography. These landslides dammed up the local drainages and produced the many lakes on the north side of Mount Tam that Marin residents rely on for much of their water supply. Let's take a look now at the other major process that's involved, and that is sea level rise and fall. Through most of the past millions of years, as I've said, sea level was much lower, and the bay was a dry valley. Estuaries like the bay are really drowned valleys, often river valleys rather than tectonic valleys, that are only flooded when sea level is high, as it is today. We're living in an interglacial period when there's very little snow and ice tied up on land, and most of the world's water is in the ocean. But if you go back to the last ice age, which peaked at about 20,000 years ago, this slide shows the maximum ice cover here in northern hemisphere, but it wasn't just this much ice on land, it was all over the world. And the sea level, because so much snow and ice are tied up on land, sea level was about 100 meters, or about almost 400 feet lower than it is today. The Sierra Nevada had an ice sheet on it that was about 400 miles long, and the ice over layer of ice in ice sheet and glacier over, say, Tuolumne Meadows was over a mile thick. So this was not a small thing. I'm sometimes asked about whether there are glaciers here in the Bay Area. You know, you see these big valleys. People who've come from areas, Seattle area particularly, and others where water bodies like Puget Sound are formed by past glaciers. And they ask, well, was San Francisco Bay Valley carved by a glacier? Well, it was not. There was never glacial ice. Probably, well, I don't know about any, well, probably not much ice at all in the Bay Area. But we certainly had the effects of the Ice Age in the Bay Area because it drained the bay of water. When sea level fell 400 feet, the shoreline was out here beyond the Farallon Islands, and the rivers drained enormous river system. Look at this, Sacramento San Joaquin River. It had cut through Carquinez Straits and through Raccoon Straits, cutting Angel Island off from the Tiburon Peninsula, where it was used earlier joined, and flowing out over the continental shelf, which was dry land. And you could have taken a bicycle ride on a nice sunny Sunday, Saturday, or Sunday ride from your home in the East Bay or anywhere in the Bay Area out 20 miles or so, 15, 20, 25, for a picnic on the Farallon Ridge, looking out at the ocean to the west. All of this that you see was dry land at the time. Note also here that the drainage system in the South Bay was along the west side of the bay, now down the center. This too is a function of the interaction and the movement along the faults in the Bay Area, because the South Bay bedrock is tilted slightly to the west and is going up more on the east. Remember, we're going up over here on this side, and that has moved the drainage over to the west side of the bay. Now look again at this slide and take the water out and put the Sacramento, San Joaquin rivers here. They've cut a channel that right through here and right along the shoreline here is about 100 feet deep. I wasn't really aware of how close to shore this channel and these rivers came. They cut right along the edge here until I went on one of these Oakland Museum cruises with Marilyn last, fall or spring? Yeah. And on the last one, we went out. I kept my eye on what's it called on a ship? The depth meter. And as we sailed around, we came on this last cruise from the Golden Gate and sailed past here. All the channel runs right up against shore here, about 100 feet deep. More surprises that you really just aren't aware of when you look at the bay. So think about this next time you're out looking at the bay or over the bay. Think about or on Angel Island, the roar of the water. Remember how shallow the rest of the bay is. So think of this snow melt in summer from the glacier, the 400 miles of snow and ice on the Sierra, pouring down through here. The volume of water must have been absolutely enormous. And it's cascading down from the shallower parts of the system down into this deep canyon that gets to be 364 feet deep just west of the Golden Gate Bridge. So the roar for the Native Americans who were probably here during these ice ages, last one must have been enormous. Well, the waters went out, and then starting about 18,000 years ago, the waters began to rise again, and you can see here its progress as it entered the Golden Gate about 8,000 years ago and began to flood the valley that had been dry. And if you've got really sharp eyes and remember a slide or two back, you'll catch an error that our drafts person made in putting together this figure. Anybody see it? No, look right here. Whoever drafted this didn't know that the channel goes through Raccoon Straits and put it around the wrong side of Angel Island. I didn't catch it. I had to review all these graphics, and man, I spent a lot of time on it. I didn't catch it. In fact, I didn't see it until I was putting together this program. So for the last 3 years, I've been looking at this and saying, oh, great figure, and not catching that. But I thought, I'd see if any of you saw that. Interesting, these little details. All right, so here you go, sea level rising. And if it works, the next slide will be an animation of this process that was done by Tanya Atwater of UC Santa Barbara, who does absolutely marvelous animations. She's got animations of the plate movements over tens of millions of years, changes in western U.S. tectonics and so on. And if you Google Tanya Atwater, UCSB, or just Tanya Atwater animations, you will see a whole list of them. She was one of the first people to start animating plate movements, and she's done a wonderful job. So let's see if it works. Come on, baby. Jen, how do we... Oh, wait, let me push this one. Where's Jen? Let's put the movie. It worked when we tried it. It's not working now. Oh. Oh. Yeah. Technology takes patience. We tried it before and it worked beautifully. Yes? And stay here and let's run it one more quick time. Let's run it one more time. Starts slow and then speeds up. And about 6,000 years ago, the bay reaches more or less its present configuration. and it's full. Okay, so my PowerPoint quit, so we're going to have to start that one over again. Can you, one more time? I know. Can you start it? So, Tanya Atwater animations. Now, if we can go back, we're on 21, slide 21. No, 21. No, go back. Sorry. Okay. All right, now it's working. Oh, all right. One more time. I can't go to the next slide until it finishes yet again. But I think you now get the picture, right? You could have gone out to the Farallons and had and there we go. All right. Now, that was the latest rise in sea level after the Ice Age that peaked about 20,000 years ago. And what if we go back now further in time? We can look at the bay's history through cores that have mainly been drilled for engineering studies for the bay's bridges. And here you see in March of '98, the Caltrans crew, their contractors, taking cores at the east side of Yerba Buena Island to look at the materials where they want to anchor the new east span of the Bay Bridge. And my colleague Mary McGann and I were collecting samples. We talked to Caltrans and got permission to go out on this drill rig and collect samples as they were bringing the core up from beneath the bay. And what you get are long cores that we cut into chunks like this. It's mud. The top part really soupy, goopy stuff. But as you go down further, it's been dewatered and gets firmer and firmer. And when you wash away the sediment in sieves, you are left with the remains of the organisms that lived in this mud or whose skeletons drifted down from the water column when they died. So we have a whole range of organisms that we can look at, and each of the organisms has its own preferred environment. The ones that live in the mud may like the shallow or the deep. They might like cold water, warm water. Sharks, for example, you don't begin to see shark skeletal material until the bay reaches a certain salinity, when it's starting to fill and you have just a lot of fresh water coming in. It's too fresh for sharks, so you can look at when you pick up sharks. So these materials can tell you, these skeletons and organic particles, a great deal of what's going on. These are little single-celled animals called foraminifera, the kind that I and others have worked with in the paleontology department and worked with Jerry Lips on. And each of these has their preferred environment. So Gunterite here, Ophidium gunterite likes warm and shallow muds, whereas this Ophidium likes colder, a little colder and deeper, and so on. So by looking at the distribution of these organisms in the mud, we can get a picture of what's going on underneath the bay. Now, this is what we learned, and most of this work was done originally by Brian Atwater when he was at the USGS in Menlo Park now it's at the UW in Seattle. And he looked at cores from what was then the proposed San Mateo Bridge. And he went down through those cores, sieving away the sediments and looking at the organism. And he recognized that there were alterations of estuarine and alluvial deposits in the South Bay. These greenish layers are estuarine. Are the muds that are being deposited in the bay today. B are the muds that were deposited during the last interglacial, 125,000 year ago one. It's a very long period, a lot of sediment coming in. The orange layers are when the bay was a dry valley and mostly a grassland. The yellow here are dune sands that blew across San Francisco. Same dune sands that underlie 2/3 of San Francisco, in fact. And you can see from this cross-section at the San Mateo Bridge that there are at least 4 times that recorded that have been estuaries. Maybe as many as 7, because we don't know how these 3 correlate with these. So E could be the same one as C, or F could be the same one. We don't know where G fits in because the cores, unfortunately, didn't go down far enough. It would be marvelous to be able to drill a core all the way down today and get an answer. But without an economic need like a bridge to do so, it isn't going to happen. These cores also didn't go all the way to the bottom of the bay. There was an ash layer here in this one that was dated at 570,000 years. And it tells us that at that time, there was water in this valley. And there's been some more recent work on the Alameda side of the bay that suggests that the bay may actually have been, the valley occupied as long as a million years ago that we can record. But it isn't really known when the drainage from the Sierra and the Central Valley cut through the Bay Area. We know that 5, 6 million years ago, 7, the drainage was down through the southern end of the San Joaquin Valley until that drainage was cut off by the movement along the San Andreas Fault. So somewhere in the last few million years, the drainage has started to come through the bay, as you can see here. Well, my research was on Unit B, the last interglacial, and I got a rather interesting picture from the microorganisms, particularly the foraminifera, and some single-celled plants called diatoms, of what that bay looked like. And what I found was that it was a much larger bay. We know that sea level at that time was about 20 feet, 6 some meters higher than it is today. You can see here the present shoreline, and what we inferred was the shoreline at that time during the last interglacial. There's evidence for this shoreline along much of the perimeter here in cores that have been drilled down with get into this estuarine mud from 125,000 years ago. And both Dana Wagner, who was a paleo PhD, and I looked at cores from this area along here. My area was to look from Alameda to Hunters Point at the proposed course for the proposed southern crossing that never got built. And we found the forams over here and other organisms at that time were of the kind that today you only find out along the coast, north and south of the Golden Gate. And that tells us that this bay had more marine conditions and that the higher energy along the east shore of that bay. It's a little hard to visualize how that enough marine water it was higher sea level could produce those conditions if only the Golden Gate were the seaway between the bay. And in fact, there are sediments down here on the peninsula that indicate that there was another seaway, that San Francisco was an island at that time, and that the ocean waters came in not just through the Golden Gate, but also through the Colma Strait, and that circulation was enough to produce marine conditions where today we have more estuarine ones. So very interesting what this bay from not too long ago could tell us. And as I say, we can infer from the organisms living in those muds that it was not only larger, but colder and more saline. So the real question is, and the question for the rest of the talks today, is this where we are heading? Back in the 1980s, the Chronicle, and this work that was done that produced this, Brian Atwater's work was published in 1979. A few years later, the Chronicle did an article on what would happen with that kind of sea level rise in San Francisco Bay. And you could see what it does to San Francisco, and you can imagine what it would do to the South Bay, the margins of the bay. You will hear more about that later this afternoon. And maybe even this. Not likely to come to this, certainly, but lots of questions about what the sunsets are going to look like in 25 or 50 years. Thank you.